So last order of business today, finding the area under the curve using a z-table in order to find the probability of getting an outcome within a certain range of values. So I'm just going to start by redrawing the example probability distribution that we've been working with, which is the number of thefts likely to occur in a store over the course of a month, which has a mean of 65 and a standard deviation of 15. As we figured out before, you can mark off 1, 2, and 3 standard deviations on this table, and you get 80, 95, and 110 for 1, 2, and 3 going in a positive direction. And you get 50, 35, and 20 going in a negative direction. So far, I'm not putting anything new up here. I'm just rewriting what we had on some previous pieces of paper. And as we know, our mean here is 65, and our standard deviation is 15. But let's say we convert every single thing in this normal distribution to z-scores. So every single possible value of thefts that we have, we're going to turn it into a z-score. When we do that, we are standardizing the normal distribution, and we're turning it into a standard normal distribution. What it looks like is this. It has a mean of 0. We're counting everything in z-scores. So we have a mean of 0, where we used to have 65 for our mean. And that's because, again, your mean is always 0 z-scores away from the mean, right? Because it's right there. And then instead of having 80, 95, and 110 here for 1, 2, and 3 standard deviations away from the mean, we have 1, 2, and 3, where this is 1 standard deviation, 2 standard deviations, and 3 standard deviations. And going in a negative direction, we have -1, -2, and -3, where these are -1 standard deviations, -2 standard deviations, and -3 standard deviations. So again, we are counting in z-scores. We also know that our standard deviation for the whole normal distribution is 1, because 1 standard deviation is always going to be 1 standard deviation away from the mean. So we can write up here, our mean is 0, and our standard deviation is 1. So this is a standard normal distribution. And again, you can turn any normal distribution into a standard normal distribution by converting your different values to z-scores. And if you wanted to double check, you could always plug these values into the z-score equation, and you'll come out with 1, 2, and 3, and -1, -2, and -3. So as an example, let's use the same values that we had in the last set of examples, which were... Oh, no, scratch that. We're not going to do that. The first thing we're going to start with, because this will be one step that's a little bit easier, is the probability that between 65 and 100 items will be stolen. And the first step to answering any of these questions that I think is really the most helpful is just to draw what you're doing. So right now, we're thinking about number of thefts, and we want to know the probability that between 65 and 100 items will be stolen. If we're thinking about probability and area under the curve, what we're looking for then is the area under the curve between 65 and 100, because this area is going to correspond to the probability that between 65 and 100 items will be stolen. So in order to find this probability, our first step is going to be to convert everything to z-scores. So these values that we're interested in, we want to find the z-scores for them. The first one, 65, is the mean. So you should know what this is going to come out to be, but I'll go through it anyway. So we want to find a z-score for 65. Our z-score formula is the same as it was on the last piece of paper. So we have x minus mu over sigma, or our value of interest minus the mean divided by the standard deviation. Here, our value of interest is the same thing as the mean, so we'll be plugging in 65 for x, 65 for mu, because that's the mean as well, and dividing by 15, which is our standard deviation. 65 minus 65, of course, is 0, so you end up with 0 over 15 and a z-score of 0. So this should track. For 100 thefts, though, we still don't know what this z-score is going to be. So we'll plug everything into our formula. Now for x, we have 100, and we're going to subtract 65, which is the mean, and divide by 15, which is the standard deviation. So if we do this math out, we'll get what we had on that last sheet, which was a z-score of 2.33. What this means is that you can redraw this distribution now as a standard normal distribution, where everything is counted in z-scores. So our mean here is at 0. And our value of 100 thefts here is at 2.33. And if you remember, on the standard normal distribution, everything is the same. The only thing that's different is that we're now counting in z-scores instead of thefts. So it's like converting from feet to inches. We haven't changed the shape of it. We haven't changed any properties of it. The only thing we've changed is how we're counting. So now instead of counting in numbers of thefts, we're counting in z-scores. And we still want to know the area under the curve between 0 and 2.33 z-scores here. Once we find this area, we'll automatically know this area because, again, every single thing is the same between these two things except what we're counting in. So the shape of it is the same, and that means that the area under the curve between this value and this value is the same as the area under the curve between this value and this value. But because this is a standard normal distribution here where we're counting in z-scores, the areas under the curve have already been calculated long, long ago, and they're listed out in different places for you to see. So all we need to do to find this area is look it up on the z-table. Unfortunately, now we're coming to the most awkward part of this lecture, and something I discovered today is that I no longer have any paper copies of a z-table left over, and I also don't have a printer in my house where I'm recording all of these lectures. So what I'm going to do is I'm going to stick my computer under this camera and hope for the best here. So please bear with me, and we'll see how this goes. So a z-table is like computer inception here, and let me see if I can actually get it to. Okay, cool. Sort of getting there. Except that we're upside down. Hang on. You would really think that I would have figured this out before I started recording this lecture, but I didn't. So please continue to bear with me. Okay, so this is what a z-table looks like. And this is what I'm going to be posting to Blackboard for you to use in the problem set. So what the z-table shows on it are different z-scores and the areas that correspond to each one. This little purple box here says z, and then we have numbers going down in this column and then out towards the right. What these numbers show you are the first two digits in your z-score and then the third digit in your z-score. So if we're looking for a z-score of 2.33, we're going to start by going down to 2.3, and then we're going to go over 3 more to get to 0.03. So we got 2.3 plus 0.03 gives us 2.33, and that means that the value where these two things intersect, where you have 2.3 and then 0.3, that's the area under the curve between the mean and a z-score of 2.33. So again, the first two digits here are going to be the first two digits in your z-score. With a z-score of 2.33, our first two digits are a 2 and a 3, so it's 2.3. Our third digit, 2.33, is also a 3. So we're going to go from 2.3 and we're going to go over here to this 0.03. Where these two things intersect, which happens to be a value of 0.4901, is the area under the curve between the mean and that z-score. So I'm going to go back over to the page now. And again, I apologize for literally everything that's happening right now. Okay, so we're going to go back over here, and we're going to finish answering this question. So we use the z-table to look up the area under the curve between our mean of 0 on the standard normal distribution and a z-score of 2.33. And again, we did that by looking it up on the table, the 2.3 in the column, and then the 0.03 in the row. When we did this, we came up with an area of 0.4901. So on a standard normal distribution, there's an area of 0.4901 in between the mean and a z-score of 2.33. Good news! That's all you need to do. So once you've found this area, you know that the area under the curve between 0 and 2.3 is equal, 33 is equal to 0.4901. Because everything about this normal distribution is the same except for the units, we also know that the area between our mean and 100 thefts is equal to the same thing. Because again, it's like converting from feet to inches. The only thing that's changing is the units that we're counting in. So here we're counting in z-scores, here we're counting in number of thefts, but everything else about it is the same. So if this area is 0.4901, this area is also 0.4901. And now we have an area under the curve between two values. The area under the curve between two values, as we've seen earlier, is also equal to the probability of getting an outcome between these two values. So we can say that the probability that between 65 and 100 items will be stolen is equal to 0.4901. Or in other words, there is a 49.1% chance that between 65 and 100 items will be stolen. All right, so that's how you can use z-scores to find the probability of getting an outcome between two values. And I'm going to go through one more example now that shows how to do this when you're not involving the mean directly. So when you are looking for the probability of getting values, and one of those values is not the mean. So let's say, for instance, that you want to find the probability that between 60 and 75 items will be stolen. So I'm going to draw out our main probability distribution here again, where we're looking at number of thefts. And we want to know the probability that between 60 and 75 items will be stolen. So here our overall mean is 65, our standard deviation is 15, so we've got 65 here. Our standard deviation is 15. And we're interested in finding the probability that between 65 and 75 items will be stolen. 60 and 75. So in other words, we want to know the probability that we'll have an outcome between these two values. In order to do that, we're going to have to find the area under the curve between these two values. So I'll write this out. Probability that between 60 and 75 items will be stolen. Our first step is going to be to convert everything we have into z-scores. So in other words, we're going to standardize this normal distribution. To find our z-score for 60 thefts, we're going to once again use that z-score formula where z is equal to x minus mu over sigma. And we're going to plug in 60 for our x, that's our value of interest. We're going to plug in 65 for our mean and 15 for our standard deviation. If you do this, you get negative 5 over 15, and that comes out to negative 0.33. So your z-score for 60 is going to be negative 0.33. We'll do the same thing for 75. So we plug all this stuff in. Our value of interest is 75. Our mean is 65, and our standard deviation is 15. So here you get 10 over 15, and that comes out to 0.67. So now we have z-scores. Our second step is going to be to standardize everything and then find the area under the curve for those values. So we're going to convert everything to z-scores. And again, this is like converting from feet to inches. The only thing we're changing are the units that we're measuring in, and everything else about this, including the shape of the distribution and the area under the curve between these values, is going to stay exactly the same. So here our value of 60 thefts is converted to a z-score of negative 0.33. Our value of 75 thefts is converted to a z-score of 0.67. And again, this is not drawn to scale. And we now have a standard deviation of 1 because we have a standard normal distribution where our mean is 0 and our standard deviation is equal to 1. That's always going to be the case for any standard normal distribution. Our next step is going to be to find the area under the curve between these two values. So what you might remember from the z-table, and here we go again, is that the z-table, my computer hates me right now, and so do all of you, and I know that. So what the z-table shows you is the area under the curve between 0 and some value. So it doesn't show you the area under the curve between some value and some other value. So in order to answer this question, we're going to have to do it in 2 steps. And specifically, we're going to find the area under the curve on one side of the mean, and we're going to find the area under the curve on the other side of the mean. And so the nice thing about working with a normal distribution is that it's totally symmetrical. So what's under the curve between 0 and negative 0.33 is the same as what's under the curve between 0 and 0.33. So what we're going to do is we're going to use the z-table to find the area between 0 and 0.67 and between 0 and negative 0.33. But to do this, we're just going to ignore this minus sign and treat this like it's 0.33. So again, we're going to be using that z-table, and we're going to use it to find this area, and we're going to be using it to find this area right here. Once we find these two areas, we'll just add them together to find the total area. So we'll just treat it like a shape, where if you add one area to another area, you get the total area. So in our second step of finding the area under the curve and the standard normal distribution, we're going to find the area for z equals 0.67, because that's going to tell us what's in between 0 and 0.67, and what's the size of this area that's between those two values. So when we look on the z table, we want to think about our first two digits here. In this case, it's 0.6, and then our next digit is a 7. So we want to find the area for z is equal to 0.67. We're going to be looking at 0.6 for our first two digits on the z table, and then we'll be looking at 7 for our third one. To find the area for z is equal to negative 0.33, we're going to be ignoring that minus sign because our normal distribution is symmetrical, so what's between 0 and 0.33 going in a negative direction is the same as what's between 0 and 0.33 going in a positive direction. And we're going to be looking for (0.33) on the z-table, where again, what's here is going to be in the column, and what's here is going to be in the row. And that's the same for both of these. So, one last time with this nonsense. You guys have no idea how much I'm kicking myself for not somehow printing this thing, but it's too late. So we have to find the area under the curve for these two different z-scores. There's between 0 and 0.67 as our first z-score of interest. So we're going to look at 0.6 here as our first two digits going in the column, and then we're going to go all the way over to 7. And that gives us an area of 0.2486, which I'm circling here with my pen. So I'll write 0.2486 next to 0.67. Right, our next area that we're going to be looking for is the area that corresponds to a z-score of 0.33. So we're going to go down to 0.3 in the column, and then we're going to go over to 3 here. And if you go 0.3 over to 3, then you get an area of 0.1293, which I'm, again, circling with my pen. So I'm going to write that down as well. So we're almost to the answer and the end of this problem. We now have areas under the curve in a standard normal distribution that are between 0 and 0.67, which is 0.2486, and between 0 and negative 0.33, which is 0.1293. To find the total area under the curve, we're just going to add these together, because that'll tell us what's under here and what's under here. So in this case, we add together, and when we add them, we get 0.2486 plus 0.1293. And that comes out to 0.3779. That means that this total area under the curve is equal to 0.3779. So the total area equals 0.3779. Well, we know that our standard normal distribution is the exact same shape as our normal distribution that we're working with here, and that the only thing that's different is that we change the units on the bottom. This means that our total area on this normal distribution is also equal to 0.3779. And once we know the area under the curve between two values, we know the probability. So if there's an area under the curve of 0.3779 between 60 and 75, it means that we have a probability of 0.3779, or 37.79%, of getting a value between 60 and 75. So we would say that there is a 37.79% probability that between 60 and 75 items would be stolen. And we are to the end of this problem. And as a quick note, there are other combinations that you can do here to find the probability. So if both of your lines were on one side of the mean, for instance, you could find the probability between those two. You could find the probability between, some value and either end of your distribution. And we're not going to go through those examples now. I guess they're fun brain teasers if you want to think about it. But the point of today is to demonstrate that you can use normal distributions to find the probability of obtaining an outcome between two values, and to practice thinking in terms of area under the curve and probability, and get some experience with working with the z-table as well. Okay, so that is going to conclude my lecture today. I will end it by saying, once again, I'm sorry that I stuck my computer under my document camera, which was showing up on my computer, and then tried to draw on it with my pen. Try not to ever do that again. Otherwise, problem set is due as usual on Sunday, and I hope you guys have a great week.